This section explains the diffusion transformer model and code implementation. Let's first look at the diffusion transformer model overview. The diffusion transformer is a transformer-based model for diffusion-based generative modeling. Unlike CNN-based models such as UNet, which are traditionally used in diffusion models, DiT leverages vision transformers, VIT, to process images as a sequence of patches. Diffusion process. Diffusion models are generative models that learn to progressively denoise an image starting from pure Gaussian noise. The forward process corrupts an image x0 by adding Gaussian noise at each step as follows. Alpha t is a predefined schedule controlling the amount of noise added at each time step. The goal of the model is to learn the reverse process, which removes the noise step by step as follows. Mu theta is the predicted mean, and sigma theta is the variance. Time step embedding in DiT. Since diffusion models depend on time steps, we need a way to embed the time step t into a vector representation. DiT uses sinusoidal embeddings, similar to transformer positional encodings, to encode the diffusion time steps into a high-dimensional representation. For a given time step t, the sinusoidal embeddings are defined as follows. This generates alternating sine and cosine values for different frequencies. Multi-head self-attention. DiT leverages multi-head self-attention to process images in a non-local way, allowing it to learn long-range dependencies between patches. Self-attention. For an input sequence X, the self-attention mechanism computes as follows. Q, K, V are query, key, and value matrices. WQ, WK, WV are learnable projection matrices. DK is the head dimension. Transformer block. DiT stacks multiple transformer blocks which consist of 1. Layer normalization. 2. Multi-head self-attention. 3. Feed-forward network. 4. Residual connections. Complete diffusion transformer model. The DiT model follows the VIT paradigm. 1. Patch embedding. Converts the image into patches. 2. Time step embedding. Encodes the diffusion step. 3. Transformer encoder. Applies multiple transformer layers. 4. Final output projection. Outputs noise prediction. Now we implement the diffusion transformer code. Time step embedding class. Multi-head attention class. Transformer block class. DiT class. testing the diffusion transformer model.